Welcome to the course on Scalable Data Science. I'm Anirban. I'm from IIT Gandhinagar. Today's lecture is number 15B on QB decomposition. Today we'll talk about different kinds of dimension reduction that are applicable for large data sets. Okay? So before we go into our definitions, what are some algorithms for dimension reduction that we're looking into, let us motivate the question of dimension reduction from the point of view of machine learning applications, right? So, as you probably know, that recommendation systems, building recommendation systems is a big area of machine learning, right? And we have mentioned that if you look at sites like Amazon, Netflix, Flipkart, even Google, all of these have, generate a huge amount of revenue by being able to recommend the right product to the right person, right? The appropriate product to the right person. So imagine a particular recommendation system. Let's suppose we have data that consists of users, how a bunch of users rated a bunch of movies. Okay, so this is, for instance, the data that Amazon Prime has collected. Okay? And each entry in this matrix, maybe is a term that is a score that is based on how a particular user maybe rated a movie, how much time a particular user spent seeing a movie, so on and so forth. So we are not going into the details of how this particular data, how this particular matrix is being filled up. The big question is that this matrix is pretty big, right? Because potentially there are hundreds of thousands of users, and similarly there are hundreds and thousands of movies. Okay, so but the matrix is also very sparse because each user probably has not seen more than 100, 200 movies, even though she might be a movie buff, right? And so every row potentially has which is of size the number of movies, which is, let's say, 200,000 movies, has only 200 entries potentially, right? And now this is the data that we have, and we might have some additional data on the user profile and the movies and the movies, but let us disregard from that from now, right? The question is that based on this user movie data, what we have to see is that a user for whom we have some data about let's say this particular user, and we know that she has liked these movies, she has not liked these particular movies, and so on and so forth, right? And we have some rating on these movies by this user. So what should I suggest this user, right? What movie should I recommend this user to sort of see, right? And you can potentially imagine that the better the recommendation system, the more the users are likely to come back to the site, right? Because it takes time to search through the movies of the site. So if I can actually recommend the user, right, that this is the movie that I think that you're going to like best, the user's enjoyment is likely to increase, and she's likely to come back to the site again and again. Okay, so this is what we really want, right? That we want to really sort of try to predict that what is the movie that the user is going to like best. Okay, so the way this is formalized is that we kind of imagine that this particular data, the user movie data, has some structure, right? Because otherwise we cannot hope to learn a model, right? We cannot hope to predict the missing entries from a model. Okay, so what is the kind of structure? So here is one typical assumption about the structure. We assume that the users have preferences, right? Let's say that there are different genres. Let's say that one of the genre could be romance, one of the genre could be action, one of the genre could be drama, and so on and so forth. And the users, suppose, have different preferences over these genres, right? That maybe I like to see drama movies 30% of the time. I have so much preference over drama movies. I have so much preference over action movies and so much over romance movies. Okay. Similarly, the movies can also be characterized in terms of belonging to genre or a mixture of genres. Okay, so what this kind of implies, what this gives an intuition of, is that maybe there is a low rank structure in this data, right? So how exactly the low rank structure manifests itself in generating the data is a question about the generative model, and we're not going to go into the details of it, right? But at the end of the generative model, the optimization problem for learning the model typically boils down to this, that we want to decompose the existing user movie data in terms of the product of two low rank matrices, right? One that we call the user versus topic, right? And the other is the topic versus the movie, right? I am writing topic in quotes because I'm not guaranteeing in this particular model, in any such model, that these topics are interpretable, in the sense that these topics correspond to the real movie topics that we understand. One of these topics might be a mixture of many of the human understandable movie genres, for instance, right? But nevertheless, right, that might not be so important. This user interpretability might not be so important from the point of view of being able to predict well, right? In terms of the model, what we are really saying now is that, let's say that Aij, right, is the entry, is the value of the rating that the ith user gave on the jth movie. This now, right, we are writing it, we are trying to model it as a product of two things. We're trying to model it as a distribution of the user I over the different genres, which is given by this particular by the ith row of the matrix X. This is, let me call this the matrix X, let me call this the matrix Y. Okay, so then the entry Aij, right, we're trying to model it as the product of the ith row of the matrix X and the jth column of the matrix Y, right? So the jth column of the matrix Y corresponds to, in some sense, a sort of description of the movie in terms of the hidden topics or hidden genres. Okay, and now what we're trying to find is that what is the best X and Y, what are the best low rank X and Y, right, that explain the data, right? Or rather, what are the X and Y, find out X and Y that are constrained to be low rank such that the best explain the data, right? And how do we measure best? Typically it's in terms of a norm, of a matrix norm, right, of some, you have to define some loss function. One of the popular loss functions is that you take a sum over all the over all the observed entries, right? So the sum is over all the observed entries. You take the Aij, which is an observed entry, and then you take X, recall that Xi star is the row vector which is the ith row of X, and Xyj star is a column vector that is the jth row of Y, right? So I'm trying to represent Aij by Xi star dotted with Y star j, right? So this is an inner product, and then we take the L2 square loss and then we sum it up, right? So this we typically sum it up, we could sum it up over all the observed entries, right? Or we could, in that case, the problem is not really a nice linear algebraic problem. We have to resort to optimization problems. We'll sometimes do something simpler, in the sense that we'll forget about the missing entries. We'll assume that the missing entries are filled in by some constant or some, let's say, zero even, and then we'll just sum this up over all this over all the entries, over all the I and j in the matrix A. Okay. So now if the entry Aij happens to be missing, right? Then after we have learned X and Y, so first we take the training set the training values, the set of values that are provided to me in the matrix Aij, and try to find out the Xi and Yj that sort of minimize this quantity, right? And we might even assume that let's say we might even assume, and for that we might need to assume something about the number of topics k, right? Or we might resort to some kind of regularization. Right? But once we have done that, then in order to predict the missing entry Ij, right, I'll take the corresponding dot product of the row I and the column j, and that will be my prediction for the entry Ij, right? And if I want to take the highest rated movie, highest potentially rated movie for this user, then for the user I, I'll calculate this for all possible j, and I'll find out which is the j that is the maximum that the user has not seen. So find out a j that the user that the user has not seen, right? Find out a movie that the user has not seen, and that has the highest predicted value among all such unseen movies, right? This is what we would do, okay, in the recommendation system. So as you can see, that at the heart of it comes down to finding the solution of this optimization problem, right? Aij minus the product of two low rank matrices. Okay. A similar application can be seen in modeling, right? In topic modeling, for instance, we have a set of documents, and each of the documents is being represented as a vector over the set of words. Okay, and now what we want to say is that we want to understand what are the underlying topics. Okay, so again, what we do is that we say that suppose there are k hidden topics, they may or may not be interpretable, right? And the way we find out what are the best k topics is by trying to decompose the document word matrix M in terms of the product as a product of two low rank matrices, right? One of them is the document versus topics, the other is the topics versus words. Okay, and what this kind of means is that each document, this kind of also posits the, says that the generative model here is something like that each document, right, is chooses, each word is being distributed, each topic is being distributed as a distribution over words here. So this is a topic. You can imagine that this is a distribution over words. Assume that this W is suitably normalized and so on. And now each document first chooses a distribution over topics. That this document says that maybe I'm going to be 80% on politics and 20% about sports. And then it sort of mixes the corresponding topics, right, according to these weights, according to the weights out here, right, and then it generates the words, right, and then it samples the words. So again, I'm not going into the details of the generative model, but the basic point that I want to put forward is that learning the topic distribution, modeling the topic distribution from a document word corpus essentially boils down to doing a low rank, often boils down to doing a low rank factorization of the matrix M, which is the document word matrix, right? And depending on the particular application, that whether we are doing a recommendation system or whether we are doing a topic modeling, we might want to put in different kind of constraints on the matrices. We might want to change the loss function. In one case, it might be the L2 square, the sum of squares. In the other case, it might have to do something with some other divergence, right? In the topic modeling case, for instance, we typically put in a non-negative constraint on the matrices A and W, right? So this is typically falls under non-negative matrix factorization, right? So one of the matrix factorizations. So then where do we come in, right? Where does the scalable data science come in? Now the question is that how do we, once we have come up with such a model of the data, how do we do these matrix factorizations? Because typically the documents, the matrix that will be given to you, either the user movie matrix or the document word matrix will be pretty large, right? And it's very hard, and doing matrix factorization is going to be a non-trivial question. Okay, so one of the starting points, right, in trying to do such matrix factorization is actually the singular value decomposition that we have already seen, right? And the reason it sort of, and while it does not satisfy a lot of the constraints that I mentioned before, for instance, it does not satisfy non-negativity constraints, it cannot deal with missing values and so on and so forth. It does have certain very nice properties, right? So missing values, let me write down missing values here. It cannot deal with missing values. Okay, but it does have certain nice properties. For instance, as you can see, as we have mentioned, that once I write down the matrix A as a product of three matrices U, sigma, and V transpose, right? If I really want to get the optimal low rank approximation to the matrix A, right? For instance, in terms of the Frobenius norm, that is, if I want to solve this particular question, right, that I want to get the matrix X such that X is rank at most K, right, and the Frobenius norm, that is the sum of Aij, Ai minus Xij square, and the summation over Ij square root. This, if you recall, is the Frobenius norm. And if you want to minimize this norm, if you want to minimize this error under the constraint that X is of rank K, rank at most K, then the optimal such matrix X can be obtained by doing by looking at the singular value decomposition. Essentially, what you do is that you find out the singular value decomposition, right? You keep only the top K singular values, and then you keep the corresponding singular vectors on the left and the right hand side. That gives you the matrix AK. And interestingly enough, this also, if you change this norm to be something like the 2 norm, right, which is the spectral norm of the matrix A minus X, the same matrix AK also serves as the optimal solution of that. Okay, so because of this, because of such nice reasons, single level of decomposition often starts as a starting point, often acts as a starting point for such for more complicated optimization problems. Okay, for more complicated matrix factorization problems. So let us try to try to do SVD in a, I mean another problem, but the problem behind SVD is that it also has very high complexity, right? In the sense that it sort of takes time, order ND, min of ND. Right, which is like cubic, right, mean of n and d, which is almost cubic in n. Okay, and the question is that can we do faster, right? Because this is not, I mean, given the size of our data, this we have mentioned is not scalable. So for that, let us look at an alternate look at SVD, right? So one way of looking at SVD is that let us look at only the matrix U, right? So the matrix U, right, or for instance if I take the first k singular vectors of U and call it UK, that forms a basis, I mean U itself forms a basis of the column space of A, right, and therefore and UK forms a basis of the column space of AK, which is the optimal rank approximation, right. So therefore one way of looking at the matrix AK is that it can be written as UK times X, right, where X really you can write it either as sigma k vk transpose, or you can equivalently write it as X is UK transpose A, right. Basically X is then the projection of A onto the top k singular vectors UK. Okay. So then I mean AK equivalently can be written as UK transpose A. Okay, and this, if you recall, is actually a projection matrix. Okay. So the question now is that can we find such a similar decomposition but more efficiently, right? And we wish that it should retain approximately at least optimality properties that the single level of decomposition has, right? So just to sort of refresh your memory, the optimal Frobenius norm, that is the optimal Frobenius error, and let's look at the Frobenius error for now, is the one that is achieved by AK, that's given by A minus AK, which is A minus UK transpose A Frobenius square, which is given by the sum of the singular values from k plus 1 to whatever the rank of the matrix is, right, from k plus 1 to D or to R, if R is the rank of the matrix, sum of the singular values square. Okay. So what we'll do, so what we'll try to say is that we'll try to come up with a decomposition that is typically known as the QB decomposition, right? And this decomposition will look as follows. That given the matrix A, right, we'll try to come up with a matrix Q. Let's say A is n by D. We'll try to come up with a matrix Q, and Q will be n by k plus p, and a matrix B, and B will be k plus p by D, right, such that the error obtained by the error, I mean then this, so first of all it should be easy to see that QB is a low rank approximation of the matrix A, right, because the rank of QB is not more than k plus p. And what we are going to say is that the error the Frobenius error A minus QB is not much more than the optimal error A minus AK, right? It's bounded by that, right? Or we want to say that maybe the spectral error of A minus QB is not much more than the spectral error A minus AK. Remember that these two are the optimal spectral and the Frobenius errors, right? And furthermore, we also want that the size of Q, right, is not much more than k, right? And when I'm writing it to be k plus p for obvious reasons that will come out later, right? But basically I want this to be of the order of k, right? And we are looking at Q to be an orthogonal matrix, right? So think of Q as a replacement for UK, right, which is the top k singular vectors of the matrix. And once you have found out such a Q, it should be fairly obvious that the optimal B to be used is really Q transpose A, right. So therefore this QB decomposition of the matrix, we are also writing it as QQ transpose A, right, which is essentially the projection of A onto the space spanned by the columns of Q. Instead of UK, instead of projecting it on the space spanned by the columns of UK, we're projecting it on the space spanned by the columns of Q, right, and we want that errors to be not to blow up from what it was before. A different decomposition, and one that we'll look at later, is known as the CX decomposition, right? Here what we'll ask is that instead of finding out an orthogonal matrix Q, can I actually find out a set of columns C, right? So these columns, so these columns that I use in C should actually come from the columns of A, right? And still can I approximate the optimal Frobenius error, right? While choosing only of the order of k columns. And it's not even obvious that this exists as of now, right? It's not even obvious that you can choose C columns from A and still retain the optimal Frobenius norm. However, we'll show that in sort of coming lectures, we'll show that it exists, and furthermore this is actually a pretty useful decomposition, because sometimes the columns of C, right, they have special meaning. Right. For instance, remember that when we had the document, I mean, let's say that the user movie matrix, right? Now the columns of C are actually movies, right? And now if I'm finding out, I mean, a genre decomposition in terms of by actually choosing movies, then these movies are potentially good representations of each of the genres. So the interpretability of the matrix factorization comes back into the picture. That we had actually lost when trying to do the singular value decomposition. Okay, so we'll come to this later. So here is a prototype algorithm for doing the QB decomposition. Okay, it's fairly intuitive but very interesting. So what we say is that, okay, that we have a n by d matrix A, right? Let us come up with a d by k plus p matrix omega, right? And this is a random matrix. So how are we generating a random matrix? We'll come to this later. But this is a random matrix. So first we look at the matrix Y, which is a multiplication of A times omega. So that means Y is of size n by k plus p, right, which is a pretty thin matrix, right? So now doing matrix factorization of Y is actually easier, right, because it's a smaller matrix. So what we'll do is that we'll try to get the orthogonal basis for the column space of Y. Right, we'll try to get the orthogonal basis for the column space of Y, and we call that Q, right? And then we return the pair Q and Q transpose A, right? So Q is my this Q is my candidate for the close to optimal basis for a rank decomposition of A, and therefore Q transpose A is a projection of A onto that basis, right? So this is the target. This is my B. The Q transpose A is my B. Okay. So why does this work? What is the intuition? So to get the intuition of this, let's look at a setting when let's say A is of size n by d. So A is of size n by d, but suppose A is of size A has rank k, right? So the rank of A is k, which is less than both n and d, right? So imagine, let me call this shaded area the column space of A, which is the space of the span of the columns of A. So suppose omega 1 to omega k are random vectors, right, in d dimension, right? So because these are random vectors in d dimension, chosen in I mean according to whatever reasonable randomness, d dimensional randomness, we'll come to that later. The vectors, they are likely to be in general position, right, that none of them will be a linear combination of the other ones. What we can further say is that the vectors a omega 1 to a omega k, right, that is if we multiply each of these omega i's by a, these are also in general position first of all, right, by using randomness with very high likelihood, with very high probability that they are in general position. Furthermore, we also know that they all lie in the column space of A, right. So the vectors a omega 1, a omega 2 and up to a omega k all lie in the column space of A. So therefore, if I find out a basis, if I find out an orthogonal basis of a omega 1 to a omega k, right, that is also a basis for the column space of A, right, and I'm calling that Q. So any orthogonal basis of a omega 1 to omega k is also a basis for the column space of A. Okay, so then in this case it clearly works, right, that is if the rank of A is k, then the algorithm that I was proposing clearly works. What happens if the rank of A is not k, right? So imagine that the rank of A is let's say either the min of n and d, but suppose A has the following structure, that A is a rank A matrix plus some E, right, and think of E as a small perturbation. So E is full rank, but let's say that the norm of E, whatever suitable norm, and what norm is appropriate will actually in order to see that, you have to do the entire proof, which we are not doing right now. We're just giving the intuition. So let's say A is a full rank matrix, but there's a strong low rank structure. This is what we mean. So in this case also, we take the vectors omega 1 to omega k, and we multiply these by A. Right? So multiplying the vectors omega 1 to omega k by A really is the same as taking their products with respect to ak. So I look at ak omega I plus a perturbation E omega I, right? So what can happen now, right? So now suppose this is the column space of the instead of being the column space of A, this is the column space of AK. Okay, so what is happening is that AK, the part AK omega I lies in this. I mean, again, for AK, each of the vectors AK omega I, we can again still argue that they are in general position in the column space of AK. However, this perturbation can take some of these vectors a little bit outside, right? And therefore it is possible that by taking, therefore it is possible that if I look at the, if I look at the basis of A omega 1 to A omega k, right, maybe it doesn't completely capture the column, the basis for AK, right, because of this perturbation E, right? But what we can also show is that, if I take a little bit more, right, that instead of k, if I take k plus p vectors, right, then the chance that the vectors A omega I does not span the column space of AK, right, is very small, right? And this can be made mathematical, except that it's going to take it takes a little bit of non-trivial mathematics using matrix perturbation theory and so on. But we can say that, but this is really the intuitive claim, that what you can claim is that if the perturbation E is small with respect to the with the norm of AK, right, then the chance that then there's a very good chance that if you take k plus p, right, the span of the vectors A omega 1 and until A omega k plus p spans the column space of AK. Okay. So and that will again come back to my and then my previous argument again holds. Okay. So what is this random matrix? I've been talking about a random matrix, omega. So it turns out that a lot of random matrices work. Essentially any matrix omega that satisfies a JL property, for instance if you fill it up by n01s or plus minus 1s or FJLT or even sparse JL. Actually for sparse JL you have to be a little bit careful in terms of the the sparsity as well as the size of omega, but basically n01 plus minus 1 FJLT really works, right? The theoretical bounds are really the same for most of them. More or less the same up to log factors and so on. However, these differ in terms of the numerical stability issues, which means that in practice the practical performances differ significantly, right? And really for most practical implementations we use omega. As of now we use omega where every entry is coming from n01, right? There's not been enough research on the other kinds of random projection matrices in terms of empirical results. Okay. So what is the theoretical guarantee? Again, we're not going to go into the details of the guarantee, but here is essentially the claim that we can say. What we can say that if I look at the Frobenius norm bound of A minus QB, right? Remember that this Frobenius norm bound is at least A minus AK Frobenius. A minus AK Frobenius, and we can show that it's not much more than this A minus AK Frobenius. That is, it is at most 1 plus k by p minus 1 A minus AK Frobenius, and we can show a similar bound for the L2 norm error. There are a few different variants of the bound that you can look up from the references at the end of the lecture. The qualitative takeaway that you should take from this, that you should learn from this particular bound is that we need p to be a small constant, right? If I take p to be a small constant, in practice about 5 or 10 is enough. Then you get a very good approximation to the Frobenius norm bound, right? And although I stated this in terms of the expectation, we can easily apply Markov's inequalities and other things, right? So in fact, there's we can modify this algorithm in order to sort of give a better bound. So let me talk about the modified algorithm in the next slide. So just in the next lecture, just to give some references, most of this lecture was from these lecture notes from Randomized Numerical Linear Algebra by Petros and Mahoney. There's also a very nice survey on finding structure with randomness by Halko, Martinson and Trop. And if you're really looking for practical guides with MATLAB code, there's this very nice article by Shushen Wang that actually provides you MATLAB code for a lot of the matrix factorizations. And thank you.